There was no siren, no warning message, no slow buildup that gave people time to react. One moment, California's iconic coastline stood firm against the Pacific. The next, a massive section of cliff simply disappeared. Over the weekend, powerful waves slammed into the coast near Santa Cruz. Tourists and locals had seen storms here before. Erosion was nothing new. But this time, something different happened. A large portion of the cliff along a well-known coastal road broke loose and collapsed straight into the ocean. From above, it looked like another landslide, tragic but familiar. California has been losing pieces of its coastline for years. Storms are stronger, sea levels are rising, bluffs crumble more often than they used to. But when scientists began examining this collapse, they stopped cold. Because this wasn't just erosion from the surface. Something deeper was happening. Hidden inside the debris were geological clues that didn't belong there. Layers of ancient sand appeared in places where they should never exist. Offshore sensors recorded strange vibrations at the exact time of the collapse, not the sharp signals of an earthquake, not the chaotic noise of crashing waves. Something else, something slow, something deep, something unsettling. And suddenly a frightening question emerged. What if California's coastline isn't just wearing away from wind and waves? What if it's failing from underneath? If that's true, then this collapse wasn't a random event. It may have been the first visible crack in a much larger system already breaking beneath the shoreline. To understand what is happening now, scientists were forced to look far into the past. Thousands of years ago, California's coast was anything but stable. Around 5,000 years ago, large sections of the Pacific coastline experienced sudden, violent changes. Researchers studying ancient marshlands and tidal flats in northern California and Oregon drilled deep into the ground, extracting long columns of sediment. At first, everything looked normal. Dark layers of peat, fine silts, slow, quiet buildup over centuries. Then without warning, the pattern broke. Sharp layers of clean ocean sand cut straight through the sediment like a blade. These sand sheets appeared suddenly, then vanished just as abruptly. Above and below them, the calm accumulation of marsh material resumed. Radiocarbon dating placed these layers firmly in the mid-Holocene period, roughly 5,000 to 4,000 years ago. The sand told a powerful story. It contained marine microfossils and beach minerals that thinned the farther inland they were found. This pattern was unmistakable. It could not be explained by storms or seasonal flooding. It was the fingerprint of tsunamis. Massive waves had surged inland in a matter of hours, overwhelming the coastline, then retreated just as quickly, leaving behind sand where it never belonged. For centuries before and after, the land was calm, then chaos, then calm again. This meant one thing: California's coastline has been violently reorganized before, suddenly, and without warning. Farther south, the evidence becomes more debated, but no less troubling. In wetlands across southern California and northern Baja, scientists found thinner sand streaks embedded in layers of mud from the same time period. Some researchers believe these were caused by rare megastorm. Others argue they record the passage of another tsunami. What strengthens the tsunami theory is how sharply these sand layers cut into the surrounding sediment and the presence of marine microfossils inside them. These features point to sudden, high-energy flooding from the ocean, not slow erosion. Taken together, the geological record delivers a clear message. California's shoreline is not stable by default. It exists in long periods of calm, interrupted by sudden and violent change. And that history may no longer be locked in the past. Because just before the recent cliff collapse, something unusual happened offshore. In the early hours of a cold January morning, seismic instruments along southern California's coast detected strange signals. The vibrations appeared first at stations west of the Palos Verdes Peninsula. The source was offshore, about 15 miles out, deep beneath the continental shelf, at nearly 13 kilometers below the seafloor. The signal didn't behave like an earthquake. Instead of sharp spikes, the energy was slow and drawn out. Its frequency sat between 0.2 and 0.5 hertz, too sluggish for tectonic rupture, but too organized to be dismissed as background ocean noise. No earthquakes were listed, no explosions, no offshore construction. The signal lingered longer than normal microseisms and showed nearly double the seasonal amplitude. Seismologists flagged it immediately. The characteristics pointed to something happening deep below the seabed. Possibly a slow slip event, possibly the movement of pressurized fluids through fractured rock. What worried scientists most was what the signal was. It didn't match landslide patterns. It didn't match known fault behavior. Instead, it suggested a slow, unseen shift, one capable of weakening the continental shelf from below, long before any surface collapse becomes visible. By the time the cliff fell, the ground may already have been compromised, and the coastline may still be moving. When the dust settled and the ocean swallowed the fallen cliff, the real work began. Within hours, a specialized field team arrived at the collapse site. This was not a routine inspection. Every movement was logged, every step was photographed, every sample was handled as evidence, because what had just happened was no longer being treated as simple erosion. The exposed cliff face told a story no one expected. Just above the fresh break, researchers noticed a dark layer cutting across the bluff. It sat at an elevation where it should not exist. The material looked nothing like the sandy and rocky layers typical of California's coastal cliffs. It was dense, black, fine-grained. Multiple samples were taken, photographed in place, sealed, and logged with GPS coordinates. Even before laboratory testing, one detail raised immediate concern. The sediment carried a faint metallic sheen, catching the light at certain angles. That sheen shouldn't have been there. To understand what lay beneath the surface, the team deployed ground-penetrating radar across the collapse zone. Under normal conditions, radar scans reveal clean, reflective boundaries where solid bedrock begins. That is not what appeared. Instead, the subsurface was riddled with shadowed gaps, zones where radar energy scattered or vanished entirely. These areas stretched nearly 40 meters across and were centered about 18 meters below the surface. The instruments were checked, then recalibrated, then checked again. The results didn't change. Whatever lay beneath the cliff was not behaving like solid ground. If those shadow zones represented weakened or altered material, then the land above had been resting on far less support than existing models assumed. The cliff hadn't simply eroded away. It had lost its foundation. As samples reached the lab, the mystery deepened. Under a scanning electron microscope, scientists mapped the elemental makeup of the sediment. The results were immediate and unsettling. Concentrations of manganese and iron appeared far above what is typical for coastal material. Further testing confirmed the presence of manganese oxides and iron compounds commonly found on the deep ocean floor. Not near the coast, not in cliffs, but thousands of meters below the surface, where mineral crusts form slowly over millions of years. Trace elements told the same story. Nickel, cobalt, copper. Their chemical fingerprint matched deep-sea nodules, not local rock. Control samples taken from nearby undisturbed cliffs showed none of these signatures. The conclusion was careful but clear. This was not normal erosion. This was not a simple landslide, and this material did not originate here. Somehow, deep seafloor minerals had been mixed into a coastal collapse. No existing geological model explains how. As the data spread through scientific circles, concern escalated quickly. Satellite imagery and aerial surveys revealed changes that were impossible to ignore. High-resolution scans compared against previous surveys showed coastal retreat exceeding predictions by more than 300%. In some locations, over 6 meters of land vanished in a single season. Not over decades, not gradually, but suddenly. INSAR deformation maps revealed movement occurring in jagged jumps, not slow retreat. The ground shifted in bursts, then paused, then shifted again. This wasn't a minor forecasting error. It was a systemic failure. For decades, planners assumed coastal retreat would be incremental. A few centimeters a year, predictable, manageable. That assumption collapsed along with the cliff. Homes once considered safe now sit inside danger zones. Roads, water lines, and evacuation routes built on long-standing risk models suddenly no longer make sense. Nearly 8 million Californians live within 10 miles of unstable coastline. And now documents have begun surfacing. Redacted soil reports, depressed risk assessments, emergency petitions quietly filed and ignored. The question dominating public discussion is simple and explosive. Who knew the risk, and why wasn't the public warned? As scrutiny grew, attention turned back offshore. Scientists began reanalyzing seismic data from the days leading up to the collapse. What emerged was a troubling pattern. The low-frequency tremors weren't isolated. Similar signals had appeared intermittently over the past year, each time beneath the continental shelf. These signals suggested slow movement, possibly linked to pressurized fluids traveling through fractured rock layers beneath the seafloor. In rare cases, such fluid migration can destabilize entire sections of the continental margin, not through sudden earthquakes, but through gradual weakening that sets the stage for failure. If the shelf itself is shifting, then the coastline above is sitting on borrowed time. This changes everything. Traditionally, Traditional coastal erosion models focus on surface forces, waves, wind, rain, rising seas. But what if those are only triggers, not causes? What if the real danger is coming from below? A weakening shelf could allow entire coastal sections to collapse without warning. Roads could fail overnight. Neighborhoods could be lost before evacuation orders are issued. And unlike storms, these processes offer no visible countdown. No dark clouds, no forecasts, no sirens, just silence followed by collapse. State agencies now face an impossible challenge. How do you warn millions of people about a threat that science is still struggling to define? How do you redesign infrastructure for risks that don't fit existing models? And how do you rebuild trust when the ground itself is no longer reliable? For now, officials insist there is no immediate cause for panic. Monitoring has increased, sensors are being deployed, emergency response plans are being reviewed. But beneath the calm statements, a deeper truth is emerging. California's coastline is changing faster than science can currently explain. The line between natural disaster and human vulnerability is thinning. What happened at Santa Cruz may not be an isolated event. It may be the first clear signal that the rules governing the coast are no longer the ones we planned for. And if that's true, the most dangerous moments may still lie ahead. As investigators pieced together data from the cliff collapse, one reality became impossible to ignore. The failure was not random. It fit a growing pattern that California's existing coastal models were never designed to handle. For decades, coastal risk planning relied on a simple assumption: change would be slow. Erosion would nibble at the land year by year, allowing time to adapt, reinforce, and retreat in stages. That assumption shaped zoning laws, insurance policies, evacuation routes, and infrastructure placement. Now that foundation is breaking. When scientists overlaid recent satellite data with long-term erosion forecasts, the mismatch was staggering. Areas projected to remain stable for another 50 years had shifted dramatically in just months. Entire sections of bluff showed deformation patterns that suggested deep structural weakening rather than surface loss. In practical terms, this means the coastline is no longer eroding. It is failing, and failure behaves very differently. Instead of steady retreat, land remains intact until it suddenly doesn't. Stress builds silently beneath the surface, then releases in violent, irreversible collapses. No gradual warning, no visible cracks wide enough to trigger alarms, just sudden loss. This is the nightmare scenario for emergency planners. Evacuation systems depend on time to issue warnings, time to move people, time to reroute traffic, but deep structural collapse offers none of that. The window between stability and disaster can be measured in minutes. In response, state agencies began reassessing every stretch of coastline previously labeled low risk. New hazard maps were drafted using deformation data rather than erosion rates. The results were alarming. Large portions of the coast jumped multiple risk categories overnight. Infrastructure once deemed safe now fell inside potential collapse zones. Highways hugging bluffs, water and gas lines buried under unstable ground. Sewage systems designed for slow change now face sudden rupture. In some regions, evacuation routes themselves cross land now considered unsafe. That revelation forced a difficult question. What happens when the paths meant to save lives are just as vulnerable as the places people are fleeing? Behind closed doors, engineers began using language rarely spoken publicly. Terms like managed abandonment and strategic retreat surfaced in planning documents. These aren't temporary measures. They imply permanent loss of land. Entire communities may need to move. The political implications are enormous. Relocating neighborhoods requires funding, legal authority, and public trust. It also requires admitting something deeply uncomfortable, that some areas can no longer be protected, no matter how much money is spent. At the same time, public pressure intensified. Residents demanded transparency. Why were risk reports redacted? Why were warnings delayed? Why did it take a collapse for this information to surface? Officials pointed to uncertainty, to incomplete data, to the need for further study. But uncertainty offers little comfort when the ground beneath your home may no longer be stable. Meanwhile, scientists raced to understand the deeper forces at play. Attention shifted offshore, where high-resolution sonar mapping revealed irregularities along the continental slope. Subtle bulges, small scarps, features consistent with slow deformation rather than sudden rupture. These patterns suggest the shelf itself may be adjusting. In geological terms, this is dangerous territory. The continental shelf supports the coastline like a massive foundation. If that foundation weakens, surface processes accelerate dramatically. Waves and storms become secondary triggers rather than primary causes. This also raises a disturbing possibility. If shelf instability continues, landslides could occur underwater, displacing massive volumes of sediment. In certain conditions, that displacement could generate localized tsunamis, even without a major earthquake. This is not theoretical. Similar events have been documented in other parts of the world. Sudden underwater slope failures triggered waves that struck coastlines with little warning. If such a process occurred off California, densely populated coastal regions would have minutes, not hours, to react. Emergency managers are now quietly reviewing tsunami response protocols for scenarios that don't involve earthquakes, a situation the system was never designed to handle. As models fail, communication becomes its own crisis. How do you explain to the public that risks are rising but timelines are uncertain? That danger exists, but predictions remain imprecise. Too much warning risks panic, too little risks catastrophe. This tension has led to fragmented messaging. Some agencies emphasize monitoring, others stress preparedness. Few acknowledge the full scale of uncertainty. Yet the data continues to accumulate. Every new scan, every sensor reading, every after-event analysis points to the same conclusion. The coastline is entering a new phase, one defined not by erosion rates but by structural instability. And once structural instability begins, it rarely reverses. This is the moment when planning shifts from prevention to consequence management. Not how to stop collapse, but how to survive it. Communities are already adapting in small ways. Property owners reinforce foundations. Cities restrict new development near bluffs. Insurance companies quietly adjust premiums and coverage limits. But these are short-term responses to a long-term shift. The deeper challenge remains unresolved. California's coastline was built for a world where the ground beneath it could be trusted. That trust is now eroding faster than the land itself. What comes next will define how millions live with the ocean, or whether they can live there at all. The collapse at Santa Cruz was not the end of a cliff. It was a warning shot. The system is changing, the models are failing, and the margin for error is shrinking. In the final part, we look at what this means for the future, and whether California can adapt before the next collapse arrives. By the time the final reports from the collapse were circulated, one detail stood out more than any other. No one could agree on a timeline. Not days, not years, not decades. Every projection ended the same way, with probability ranges instead of dates, percentages instead of schedules, language designed to avoid commitment. But nature does not work on probability. It works on thresholds. Once a system crosses a critical limit, change accelerates, often violently and without warning. Scientists know this. Emergency planners know this, yet publicly acknowledging it would mean admitting something deeply unsettling: that the next collapse may already be inevitable. Across California's coast, monitoring networks have expanded quietly. New GPS stations track ground movement down to millimeters. Offshore sensors listen for subtle shifts beneath the seabed. Drones map cliffs weekly instead of yearly. The data feeds into models running around the clock, and those models are producing increasingly uncomfortable results. Certain stretches of coastline are showing nonlinear behavior. Instead of slow, predictable movement, they exhibit sudden jumps in deformation. A few millimeters one week, several centimeters the next. This kind of pattern suggests the system is no longer dissipating stress gradually. It is storing it. In geological systems, stored stress almost always finds a release. The question is not if but where. And that uncertainty has forced planners into a strategic dilemma. Resources are limited. Reinforcing every mile of coast is impossible. Even identifying which areas deserve priority is fraught with risk. If you reinforce the wrong place, the collapse happens elsewhere. If you wait too long, reinforcement becomes meaningless. Behind the scenes, some agencies have begun shifting focus from defense to resilience. Instead of trying to hold the coastline in place, they plan for failure scenarios. Temporary closures of highways, rapid response relocation shelters, mobile infrastructure that can be dismantled and moved. These plans exist, but they are rarely discussed publicly, because resilience implies acceptance that parts of the coast will be lost. For residents, this is a devastating concept. Homes passed down through generations now sit on land classified as conditionally unstable. Property values fluctuate with each new report. Insurance coverage shrinks. Legal battles over disclosure and responsibility multiply. And through it all, life goes on. Tourists walk the same beaches. Surfers ride the same waves. children play beneath cliffs whose stability is now measured in probabilities. This disconnect between knowledge and behavior is one of the most dangerous aspects of the current moment. Humans are wired to respond to visible threats: fire, flood, shaking ground. Slow, invisible instability does not trigger the same instincts. That's why officials fear complacency more than panic. If people assume collapse is a distant risk, warnings may be ignored when they finally arrive. Evacuation orders may come too late to matter. To counter this, some regions have begun experimenting with a new approach. Instead of issuing abstract warnings, they frame risk in everyday terms. Not increased deformation, but this bluff could fail without notice. Not elevated hazard zone, but do not stop or gather here. Simple language, direct consequences. Early results suggest this works. Public compliance improves when the message is clear, even if the uncertainty remains. Still, communication can only do so much. The underlying forces driving these changes are not localized. They extend along the entire Pacific margin. Warmer oceans, altered storm patterns, rising sea levels, and tectonic stress all intersect here. This convergence creates a perfect storm of geological vulnerability, and it is not limited to California. Oregon and Washington are observing similar trends. Alaska already lives with them. The entire West Coast may be entering a shared phase of instability, each region responding differently based on geography and preparedness. For California, the stakes are uniquely high. This coastline is not just land, it is economy, culture, and identity. Ports that move global trade, cities that define innovation, landscapes that draw millions. Losing even small portions has cascading effects. Shipping routes shift, tourism declines, infrastructure investments move inland. Over time, the coast becomes something people visit, not inhabit. That future is not inevitable, but avoiding it requires decisions that are politically difficult and emotionally painful. It means choosing where to hold the line and where to retreat, investing in adaptation instead of denial, accepting loss as part of survival. Some communities are already making these choices. They relocate buildings before collapse forces the issue. They convert high-risk zones into open space. They plan for a coastline that moves rather than one that stays fixed. Others resist. Hopping technology will offer a last-minute solution. History suggests hope alone is not enough. Every major geological disaster follows the same pattern. Warning signs appear, data accumulates, models improve, and still the event surprises us, not because it was unpredictable, but because we refuse to accept its implication. The Santa Cruz collapse was not the disaster. It was the message. A message written in fractured rock and falling land, telling us the system has changed. The countdown may not have a date, but it has started. What happens next depends not on the ocean or the earth beneath it, but on how we choose to respond while time still exists. The question is no longer whether the coast will change. It is whether we will change fast enough.